Okay, 7th grade, here we are. It's lesson 2 in chapter 5. This is probably one of my favorite lessons to teach the entire year because we really get into some cool algebra in this lesson. So let's start off with some vocab. Our first vocab word is arithmetic sequence. You may look at that and try and say arithmetic, and you'd be right, but this is an arithmetic sequence. It's a sequence that deals with arithmetic. Okay, and the definition of an arithmetic sequence is a sequence of numbers in which each term can be found by adding or subtracting a constant. Okay, the same constant each time. So our example here is 1, 5, 9, 13, 17, and the rule is add 4. So every time to get from one term to the next term, I add 4. 17 plus 4 is 21, 21 plus 4 is 25, plus 4 is 28, and I can just keep going and going and generating another term of the sequence by following the rule add 4. And this is an arithmetic sequence because we're doing some addition and we're adding the same number each time. Okay, so let's take a look at some sequences here and we'll see if we can continue them and find the rule. So my first example is -5, -8, -11. So I'm going to keep going negatives here with my terms, and it looks like my next term will be -14, -17, and -20. The dot, dot, dot at the end is an ellipsis that tells us that this sequence will keep going and going and going forever. Okay, so the rule here, it looks like we're adding 3 each time, but since we're negatives, we're actually either adding a -3, so we could say add -3, or we could say that we're just subtracting 3 each time. And that's probably what most of you would say is subtract 3. Because we're getting smaller and smaller and smaller each time by 3. So either one of those rules would be perfectly fine. Adding -3, subtracting 3, you know they mean the same thing. Example number 2 is a little bit different. First thing I notice here is that I'm changing signs. I've got a negative and a positive and a positive and a negative. So I'm assuming that my signs flip-flop each time. So negative, positive, negative, positive, negative, positive. The next thing I'm looking at is that my numbers are kind of getting smaller each time. If I'm looking at maybe like the absolute values of these numbers, so if I'm ignoring my negative signs there, 128 gets smaller to be 64. That gets smaller to be our next number. And that gets smaller to be 16. That gets smaller to be 8. So it looks like I'm actually doing some division here. 128 divided by 2 is 64. Divide that by 2 and I get 32. Divide that by 2 and I get 16. Divide that by 2 and I get 8. Divide that by 2 and I get 4. So looks like this is a division rule. Okay, so we're dividing here. We can tell it's a division rule because our numbers are getting smaller and they're flip-flopping those signs. The only way our signs can go back and forth, positive, negative, would be if we were doing a multiplication or a division problem. Because you remember multiplying a positive times a positive is a positive, but a positive times a negative, that gets us a negative, and that can cause our signs to change. So in this case, we can say we're definitely dividing by a negative number because that's causing our signs to flip-flop back and forth. And if we look closely, that number that we're dividing by is -2. Right? 128 divided by 2 is 64, divided by 2 is 32, divided by 2 is 16, divided by 2 is 8, divided by 2 is 4. Okay, so this one's a little bit tougher, but I have seen these on PSSA released content, and every year I think, wow, that's a tricky question. We should definitely make sure we go over that. Okay, which of these sequences is not an arithmetic sequence? Well, that's pretty obvious. It's example 2. It's not adding or subtracting the same thing each time. It's actually a division rule. Okay? All right, let's get into the cool stuff. This one says to write an algebraic expression to describe the nth term of the sequence 5, 9, 13, 17, 21. So I love these questions. There's a lot of algebra involved in this. Basically what we're saying is this is the first term, this is the second term, this is the third term, fourth term, fifth term. I want to know, if I keep going, is there an algebraic rule to help me describe the nth term? And n is a variable that could stand for any number that we want, helping us find any term that we want. I could put 100 in there and I could find the 100th term. 500, and I could find the 500th term. This is pretty cool. It's pretty good algebra here. So the first thing we're going to do is we're going to set up an XY table. And I like doing this with X's and Y's because we see them a lot in pre-algebra. So these numbers down here, the 1, the 2, the 3, the 4, the 5, I'm going to put them down the X side. That's going to be the position of the term. And then I'm going to match them up with the actual terms from the sequence. So the first term was a 5, the second term was a 9, the third term was a 13, the fourth term was a 17, and the fifth term was 21. Okay, so far I hope we're so good. We're just taking a table, an XY table, and we're linking the term position with the term itself. Okay? So now what we do is we need to find the rule as we go down the y side. So basically we're doing what we did in example 2. We're just finding, or example 1, we're finding the rule of the sequence. So 5 to 9 to 13 to 17 to 21, we're just adding 4 each time. Plus 4, plus 4, plus 4, plus 4. And that's going to be the rule forever and ever and ever. And if I wanted to, I could find the 50th term of a sequence by just adding 4 every time all the way up to the 50th term. It would take a while, but it'd be really hard to do that for the 1000th term. So a little algebra can help us speed this process up. So that 4 is really significant here. I'm going to take my 4 and I'm going to put it in front of the variable n. Okay, so it's 4 times n, 4 times the position. Okay, but I'm going to check my math here. 4 times 1 does not equal 5. 4 times 2 does not equal 5. 4 times 2 does not equal 9. 4 times 3 does not equal 13. 4 times 4 does not equal 17. 4 times 5 does not equal 20. So what I have to do is I have to go up and I have to actually find what's called the 0 term. So what would my y be if x was 0? So I added 4 to go down my list. I'm going to subtract 4 to go up my list. 5 minus 4 is a 1, a positive 1. So I'm going to add 1 to the end of this expression. And that's the algebraic expression that describes my sequence. So what we're saying is we can take 4, multiply it by the position, and add 1, and we will always get the term on the y side. Let's check it. 4 times 1 is 4, plus 1 is 5. 4 times 2 is 8, plus 1 is 9. 4 times 3 is 12, plus 1 is 13. 4 times 4 is 16, plus 1 is 17. 4 times 5 is 20, plus 1 is 21. So any term in that sequence can be described by this expression here, 4n plus 1. We could also use x if we wanted to, if you wanted to use that variable x, but because of the way this question was written, we're going to use n. So example number 4 ties into example number 3. It asks us to find the 50th and the 1000th terms in the sequence. And that sounds really intimidating, but it's not. Check this out. We use that algebraic expression 4n plus 1. We're going to first find the 50th term, so we substitute 50 in for n. Don't forget your plus 1. Sometimes 7th graders forget that plus 1. 4 times 50 is 200. And if you add the 1, you get 201. So the 50th term in that sequence will be 201. You could check me. You could test it. You could go up to my sequence and just keep adding 4 each time to see if you get to the 50th term. But I'm telling you, this is a much faster way, right? I want to try the 1000th term now. I'm going to change colors here. The 1000th term, 4 times 1000, right? 4n plus 1, substitute 1000 in for n. 4 times 1000 is 4000. Add the 1 and you get 4001. So the 1000th term of that sequence is 4001. Isn't that cool? That's called finding the nth term of the sequence, or it's writing an algebraic expression to describe the sequence. I have another example here for you, and then we're going to be all finished with this one. I do encourage you to go back and watch what we did in example 3 again. Okay, watch what we did. Make sure you're good on that, because that can be a little bit tricky. Number 5 kind of goes with what we just did. Number 5 says find the first 5 terms of the sequence described by that expression. So what that means is we can set up that same chart we just used, x, y, and we want to find the first 5 terms. So we want to find, what do we get for y if we put in a 1, a 2, a 3, a 4, and a 5 into this expression? Okay, so 15 times 1 is 15. Let's get caught up here. I don't want to not show my work. 15 times 1 is 15, minus 20 is negative 5. So my first term of that sequence is negative 5. Next, we have 15 times 2 minus 20. 15 times 2 is 30, minus 20 is positive 10. I'm not going to show my work for the rest of these. I'm just going to do these really, really quickly. The third term is the 3 goes in for n. 15 times 3 is 45, minus 20 is 25. 15 times 4 is 60, minus 20 is 40. 15 times 5 is 75, minus 20 is 55. So if they ask us for the first 5 terms of this sequence, we take our y column and we write it in sequence notation: 5, 10, 25, 40, and 55. There's our final answer for that one. Okay, go ahead and do your practice problems for 5.2. Ask any questions that you have tomorrow in class. This is a really cool, important lesson. I can't wait to hear what you have to say about it.